So in the last class, we have looked at the plastic zone in front of a sharp crack. So we have looked at the shape of the plastic zone, for example, in plane strain or plane stress, in which case the characteristic length of the plastic zone, say let's say this is 2 rp, is small. So rp is much smaller than capital R, where capital R is the zone of K dominance for this particular problem. Now this is R. This is called the small scale yielding assumption, and what it means is that outside the plastic zone, just as you step out of the plastic zone, you still have the K field valid in the region between Rp and capital R. So that is your small scale yielding assumption, and the outcome of that is whatever happens within this plastic zone, the stresses and strains inside this plastic zone are governed by the K that you have imposed at the outer boundary of capital R, and the plastic zone size Rp is proportional to K1 by sigma y square. So this is a length scale that crops up from the small scale yielding analysis, and your all estimates, Tresca, von Mises as well as Dugdale model, tell you that the plastic zone size, the size of the plastic zone, is proportional to K1 by sigma y whole square. Now this is your small scale yielding assumption, and based on this assumption, we are going to look at two things. One is how does this affect the testing of K1C? So K1C is a parameter that has to be determined from experiments. So you will have to determine K1C from experiments, and at failure, when K1C is reached, when K1 is equal to K1C, your plastic zone size will be proportional to this quantity. So this is the plastic zone size at the point of crack initiation. Now, if this is too large, then obviously your linear elastic fracture mechanics concepts that you have applied are not valid, and therefore you don't have a proper K1C in place. So we have to check whether K1C by sigma y whole square is a large number or a small number. It's a large distance or a small distance. So this idea of small scale yielding has a bearing on experimental determination of the fracture toughness. So fracture toughness can only be determined when small scale yielding assumptions are valid. There will always be a plastic zone at the crack tip because the stresses are infinite according to LEFM. Infinite stresses cannot be sustained at the crack tip. So there must be a plastic zone. But even when there is a plastic zone, if small scale yielding assumptions are valid, then a K1C can be determined. Though K1C is a LEFM concept, it can still be determined when there's a plastic zone, provided small scale yielding assumptions are valid. So that is what we will check first. The second question that comes is what happens if small scale yielding assumptions are not valid. So if small scale yielding assumptions are not valid, or you have large scale yielding, then you don't have an elastic zone. You don't have capital R in which your LEFM fields are valid. In that case, the crack tip has to be analyzed by elastoplasticity. We have done it using LEFM. We cannot do that. We have to do it with elastoplastic fracture mechanics, or EPFM. So to go into EPFM, most of you are not familiar with plasticity theory. So we will have to do a little bit of plasticity theory, which we will do for the next 4 or 5 lectures, and that's what I will start off in the second part of this week's lectures. So let me first look at the first question, which is how does the idea of small scale yielding affect fracture testing for K1C? How does it affect the determination of the fracture toughness? Now, to do that, we have to see how fracture toughness is determined. We generally determine what is known as a plane strain fracture toughness. I have already told you that plane strain is valid if plane strain plastic zone is smaller than the plane stress plastic zone. Towards the outer free surfaces of the specimen, you have close to a plane stress situation, whereas deep inside the specimen you have a plane strain situation. So our and the fracture surfaces that you get in thin specimens, which are thin in breadth, is not the same as you get in case of thick specimens. So we have looked at this picture, if you remember. We have looked at this picture, and these are kind of plane stress specimens where the surfaces dominate what happens inside, and these are plane strain specimens where you get a flatter surface. You do have a plane stress effect towards the edge, but that is very small compared to the total thickness of the specimen. So it is clear that to get the plane strain fracture toughness, we need the B to be large enough. So if you want the plane strain fracture toughness, you need certain size of B. So there would be some specimen size requirements. The other question that arose in one of the discussion hours also is how do you prepare a sharp crack? So because all that we are doing, the idea of stress intensity factor, critical stress intensity factor, and so on, are valid for a sharp crack. So how do you prepare a sharp crack? And finally, once you have done all this, once you prepare the specimen, then how do you determine the stress intensity factor and the fracture toughness of the material? That's what we will look at, and we will also pay special attention to the fact that you cannot escape plasticity at the crack tip. Plasticity has to be small, and small scale yielding assumptions have to be valid, which means that even with the plasticity, you still have an engulfing region of elasticity where your K fields are valid, and then your plastic zone size scales as K by sigma y whole square. So different kinds of specimens are used to test for fracture toughness. They are finite specimens, of course. Remember, all that we have done, Williams solution and all, are for infinite specimens, infinite bodies where the crack tip is not close to any of the boundaries. Obviously, that's not possible. So you have the standard specimens. One is a 3-point bend specimen. The other is a compact tension specimen. It's also called edge notch specimen in tension. So these specimens have breadth, which is B, and then this is subjected to a line load. So the line load has to be applied exactly at the middle over this crack tip. And the standards, the ASTM standards, suggest that your supports, this has to be simply supported, so your supports are placed at a distance of S apart, whereas 4W is your at least 4W, where W is the width of the specimen, W is this, at least 4W is your span. Similarly, you have for the CT specimen. For the CT specimen, tensile loads are applied right above the crack. So the way this is done is 2 pins are inserted. A pin is inserted here, and a pin is inserted here, which is longer than B. So the pins actually jut out from the front and the back, and those pins are held to pull the specimen in mode 1. So both of these are mode 1 specimens, and what you are aiming to determine is K1C, the mode 1 fracture toughness from these kinds of specimens. Now the crack length has to be between close to half the width of the specimen, between 0.45 and 0.55 in all cases. This is to prevent the crack tip from interacting very strongly with either this boundary or this boundary. So we want to simulate as much as possible a crack tip that is not under the effect of boundaries, which will ensure that our LEFM fields, which were derived in the Williams solution, for example, for a crack tip residing in an infinite body, that those assumptions are valid to the extent possible. So we want this crack tip to be far from the free boundaries, and the suggestion from the standards is that it has to be roughly half the width of the specimen. So these conditions have to be fulfilled. You have to make these specimens, and then the question arises is, how do I get this sharp crack? To get this sharp crack, we first cut a notch, which is easy to cut. You have special notch cutters with which you can cut a notch, and then we cycle this through what is known as a pre-cracking procedure. So the pre-cracking procedure is that you apply if you're doing it for the 3-point bend specimen, you apply an oscillating load which is much lower than what you are finally going to subject the sample to. So you apply a small oscillating load for many cycles till this defect at the notch. So your notch is of this shape. This is a region of stress concentration, but it's not exactly a crack. But if you cycle this load at a low amplitude but over many cycles, you will have a fatigue crack that emanates from this tip, from this stress concentration point, and this fatigue crack will be the sharpest possible crack that you can make in this sample. So this is called fatigue pre-cracking. This has to be done very carefully, and you have to monitor this fatigue crack so that you stop just when it has grown enough. Otherwise it can grow too much and fracture your specimen and you lose your specimen, and then your effective crack length will be from here to the end of the notch. So this would be your effective crack length, and your effective crack length has to be roughly about half the width of the specimen, which means that you have to make the initial notch slightly lower than that, and you have to have an idea of how much of a fatigue pre-crack you can grow carefully without causing catastrophic failure during the fatigue crack growth process. Okay, so this is how a specimen is prepared, and then you have the handbook formulas. If you remember, we had the formula for the compact tension specimen. We have a similar one for the 3-point bend also, where the K, which is essentially K1 in this case, is P by B root W. W is the width of the specimen times this geometry factor. This geometry factor is fitted from finite element results. So people do finite element calculations on these kinds of geometries, and then the finite element results are fitted so that you have K1 given as P by B root W times a geometry factor which depends on the A by W, which is the crack length to the width of the specimen, and as we have seen that this is close to 0.5. So with A by W close to 0.5, you have a value of this geometry factor, and using that you can find the K1 for any load. The load is measured by the machine through which you are doing the test, these are geometric parameters which we measure at the very onset, and from the load, knowing this geometry factor, which depends only on A by W, you can figure out what is the stress intensity factor that you are subjecting the crack tip to. Okay, so this is the fatigue crack growth process. Now this notch that is cut is known as a chevron notch, and it is cut with a chevron cutter. There are special chevron cutters available, and chevron notches can be cut with these cutters in a regular cutting machine that you have in our workshops. Okay, so this is how a broken sample would look like. So what you see here is this was probably your notch. This was your notch. This is the top view of the broken surface. So you had cut the notch with the chevron notch up to here. So this part looks very smooth. Then you grew a fatigue crack up to here. So your crack length initially was this much. And then this part is the crack growth process that you went through. So after you started your experiment here, you grew the crack all the way up to here. This was the amount of crack growth that you gave, and this is how it looks like after it has broken. Okay, now there are various things that can be measured. So this is known as a clip gauge. This instrument is known as a clip gauge, and this is your CT specimen. This is your compact tension, a single edge notched. So here the pins, these are the pins. So these pins are pulled in this direction. This is your crack, and you want the plane strain fracture toughness. This is your fatigue crack that you have grown. This is your chevron notch. This is the fatigue crack. And now you are ready to start the experiment. During the experiment, generally, this clip gauge is inserted into this notch, and the opening of these two faces is measured by this clip gauge. So the clip gauge has springs, so it is closed and then pushed into this notch, which is somewhat thick, not very thick. It's less than a millimeter thick, but you can it's like a cloth clip, which you can really squeeze, push in here, and measure how much this opens during the process where you are pulling these two pins upwards. And then these loads P are measured with the opening of the opening of the clip gauge, which is called the crack opening displacement or crack mouth opening displacement. We generally call it CMOD, which is the crack mouth opening displacement, where this is the crack mouth. Okay, so this is generally plotted, and it is one of these three kinds of failure processes you will generally see. So this is one type where the crack starts growing catastrophically at this point. So the load at which the crack starts growing is noted. In some cases, you have two loads. One is PQ and one is PF. So probably some bit of crack propagation happens here. Then it either arrests, or the crack doesn't propagate uniformly across the thickness. So you have to reach this load PF before you have catastrophic crack propagation. So there are two loads, there are two shells here, and in some cases this shelf is not clearly visible, and you have a smooth variation, in which case you draw a tangent line at 5 degrees to the initial slope. You draw a line of 5 degrees, and wherever it cuts the sample, you take that value to be the value of your PQ. So either of these three you will see if your small scale yielding assumptions are valid. So we generally use according to the standards this value PQ. In this case, PQ and PF are the same. In this case, PQ is obtained by drawing this 5 degree line, and in this case PQ is clearly visible. So in either case we use PQ, and when you use PQ, you then plug PQ into this formula. So here you use PQ instead of just P. All these things are known, the geometry factor is known, then you plot the P. If you know the PQ, you can get the K1 directly. And here is one result for aluminium. This is the fracture toughness that you get from PQ. As you see that as you increase the thickness of the sample, the value from PQ goes and kind of becomes flat. This flat value is your K1C, is your K1C for this material. This is the plane strain K1C. If you do it from Pmax, then you might get a different kind of variation, but at large thicknesses, the difference that you get from PQ and Pmax generally disappear. So if you do it from Pmax, you might get a variation like this. But at large thicknesses, they kind of merge with each other and you get a unique K1C. It's easier to get it with PQ because PQ converges to the flat K1C value quicker. Okay, so these are the results for some kind of aluminium, and this is how it is done. So this gives you K1C, and you know that if K1 is greater than K1C, you have catastrophic crack growth. It implies catastrophic crack growth initiation. Okay, so now both K1 and K1C are linear elastic concepts. And how does plasticity come into this? Okay, now let us see what happens if you are testing some kind of steel. So at crack initiation, when K1C is reached, Rp will be proportional to K1C by sigma y whole square. So if you know the K1C and sigma y, let's say for steel it is 1000 MPa root millimeter and sigma y is 400 MPa, then you easily find, using the plane stress and plane strain formulas that we have derived for, let's say, the von Mises case, you find that the plastic zone size is 6.9 millimeters in plane strain and 43 millimeter in plane stress. Remember, plane stress plastic zone sizes are much larger than plane strain plastic zone sizes. On the other hand, if you use a typical glass, which is a brittle material, K1C is 30 MPa root millimeter and K sigma y is 100 MPa, then in plane strain you get a plastic zone size of only 4.5 micrometer and in plane strain of 28.6 micrometer. So in this case, in case of a glass, which is a brittle material, it's more likely that your R, which is the range of dominance of your K1C, of your Williams solution, will be much larger than the size of your plastic zone. Now, in a sample, sample that you use for fracture testing, there are standards which tell you how big RP can be. So, for example, for this compact tension specimen, for the CT specimen, the standards suggest that your RP has to be less than 2% of any of the major diameters or major dimensions of this sample. For example, B, this length, W minus A, all these things must be much greater than RP, so that your plastic zone is not large enough to interact with any of the boundaries. So it's concentrated at the crack tip, and if this condition is satisfied, you can be more or less certain that you have small scale yielding assumptions valid. Now, what you see from here is for ductile and strong and ductile materials like steel, whose K1C is high and so is sigma y, you have a situation where your plastic zone size is large. Therefore, the dimensions of the sample that you need, W minus A or B, are going to be huge. For example, if you have a plastic zone size of 43 millimeter, you would need a sample which has a crack length of order of meters. Okay, so you will have to deal with a huge sample which will be difficult to handle, which will be difficult to load in a machine, extremely heavy. So you cannot possibly enforce the small scale yielding assumptions in these kinds of materials. So you have to relax it, which means you have to allow the plastic zone sizes to be large, use thinner, smaller samples so that plastic zone sizes are large, interacting with the boundaries of the sample, and therefore to do these tests in a material, being able to do these tests in a material is a good reason why you should go for elastoplastic fracture mechanics, where the elastic fields, the K fields, no longer dominate what happens inside the plastic zone. So to understand about how elastoplastic fracture mechanics works, we have to understand plasticity a little bit. So I will spend quite a bit of time after at least four lectures uh, dealing with plasticity, dealing with the mathematical theory of plasticity, how it is framed and all, and then we will see how different aspects of plasticity are applied to um, mechanics of a sharp crack, where small scale yielding assumptions are no longer valid. This is not a course on plasticity, so don't expect a very comprehensive account of plasticity. I'm going to only cover portions of plasticity which are required to understand the results on EPFM, appreciate the results on EPFM, not more than that. For more knowledge on plasticity, you obviously have to do a course on plasticity, which unfortunately has not been offered for quite some time. So if you get interested in plasticity, you have to wait till it's offered. Okay, this will be a poor man's plasticity course, but we will go through it in some detail in the next 4-5 lectures.